a very interesting topical workshop. I've been learning a lot already in the one day yesterday. Yeah, so I was asked to review what has become known now as celestial CFT. And this is in the context of the question, is there holography in our universe? And we're all very well familiar with the situation that in spacetimes with a cosmological constant, there seems to be a holographic principle at work. And most famously, of course, in negatively curved space, the fact that we have confining boundary conditions, the under de Sitter boundary conditions, lets us study quantum gravity in a box, and that has led to an immense amount of insight into quantum gravity and black hole physics in particular. But the thing is, under the Sitter space describes regions in our universe very well that are near black holes, say highly rotating or highly charged as a toy model. While at large scales, we rather have the Sitter space. And while there seems to be some sort of holographic principle at work there too, it's more mysterious because rather than having space be emergent, time seems to be emergent. And so a good situation to look at, and which actually describes very well many processes in our universe that where we are in regions that are far away from sources, is Minkowski space, or asymptotically flat space. And it describes well the regions between black hole throats and the cosmological scale. And so the question is, does this powerful holographic principle that is at work in under de Sitter space also carry over to asymptotically flat space? And there are several questions that one has to tackle before one can really study this in a program. And as in under de Sitter space, one of the first questions is, of course, what are the symmetries here? And we have already heard a lot about the buzzwords here, which is BMS and DFS2 symmetries in asymptotically flat space. And if one manages to identify the symmetries of the bulk spacetime with those of a pure diff theory living on a boundary of this spacetime, which in this case, a natural place seems to be the conformal boundary given by null infinity, then one can ask, what is this theory living on this boundary? And this has become sort of known as pure diff celestial CFT living on the celestial two-sphere out here. And so here, if this is really a CFT, then the things that should turn up are conformal primaries and the descendants. We should be able to describe the symmetry generators by the building blocks in the CFT. There should be conformal correlators here. We should be able to compute OPEs, conformal blocks, and all the things that we are used to in CFTs like the ones dual to ADS, but perhaps in a more exotic setting. And so the end goal of such a program would be to have a non-perturbative definition of quantum gravity in asymptotically flat space, which would be extremely powerful. Okay, so what's the motivation for why this could possibly work? So it turns out that there exists a conformal basis for quantum field theory scattering amplitudes, which arises when we replace the asymptotic plane wave states by so-called conformal primary wave functions. What's behind the scenes is that the four-dimensional Lorentz group, SL2Z, acts as the global conformal group on the two-dimensional celestial sphere. And this means that we can recast four-dimensional scattering amplitudes as two-dimensional correlators on this celestial sphere. Now this is an equivalence because we are just changing from the basis of asymptotic plane wave states to the basis of conformal primary wave functions. But what we have seen so far by studying these conformal correlators is that they can put constraints on the quantum gravity S matrix. And furthermore, by having a different basis that makes different features of scattering amplitudes manifest, we might learn about new structures in amplitudes and potentially ones that we haven't already discovered. So the plan of my talk is to cover a selection of topics. This is by no means a complete picture of what's been going on of the field, but I selected some topics. So we'll start by discussing this new basis of conformal wave functions. I will then introduce what's now called celestial amplitudes at tree level. There isn't too much at loop level yet, but I will give some flavor of what's happening when you include quantum effects. I will then discuss some features of these celestial amplitudes, in particular features that are called conformal soft theorems. And then I will go to another limit of studying properties of these amplitudes, which will give rise to celestial operator product expansion. And there will be much more in Angelo's talk about that, as well as in Laura's talk about the conformal basis and the connection of soft theorems to asymptotic symmetries. And then if there's time left, I will give a bit of an insight into some other features that scattering amplitudes have, which is known as the double copy relation. And I should say, since there's a selection of different topics, I'm very happy if people interrupt me during the talk and ask, because it will be sort of a little bit changing gears between those different topics. Okay, so let me start with this conformal basis of wave functions.
Andrea?
Yes?
Sorry, what happens to the time here? I mean, you're talking about the two sphere, but null infinity also contains the time.
Right, so can you give me 2 slides so that I can show you the correlator, and then you will see that there's a 2D correlator sitting there. And we can come back to that question then. So, okay, so in the bulk, we have the S matrix where particles are labeled by the momenta, say the 3 momenta, their helicities, and then a scale, which I will take to be the energy omega, or frequency omega. For most of my talk, or all of my talk actually, I will be focusing on massless scattering processes where particles enter from past null infinity and then exit again at future null infinity. But extensions to include bases of massive wave functions reaching time like infinity have also been studied or constructed, but I will not have time to cover all of that. So I will focus on massless scattering here. Okay, so those are the labels for the scattering in the usual plane wave basis. And the scattering amplitudes have to obey, of course, 4-dimensional Lorentz symmetry. And this acts on the celestial sphere at null infinity as the 2-dimensional global conformal group, where we can now understand the scattering amplitudes as correlation functions that arise from inserting operators on points z and z bar on the celestial sphere. And these operators carry labels under the 2D global conformal group, which are the scaling dimension delta and the spin j. Let me start with giving a little bit of detail and notation. So I will be focusing on the scattering of massless particles in Minkowski space, the spacetime vectors that are denoted by x. The states are labeled by momentum null vectors k, which I will parameterize as this frequency omega, and then a null vector q. And this null vector q will be chosen to take a particular form in terms of the angles z and z bar on the celestial sphere. And these are null vectors, so k squares 0. Then in order to discuss wave functions for gauge bosons of different spin, I have a polarization vector denoted by epsilon and the polarization tensor, which I take to be the square of 2 polarization vectors. And in terms of this null vector q, they are given by derivatives of this null vector with respect to the z and z bar coordinates. And this corresponds respectively to the particles having helicity +1 or -1. Now, with that, I can now go and solve Maxwell's and linearized Einstein equations, and I will get the basis of spin 1 wave functions given by the polarization vector times the plane wave e to the I k dot x, which I will take in Lorentz gauge. So the null vector k dotted into the polarization vector is 0. And then similarly for spin 2 wave functions, I now have the polarization tensor multiplying the plane wave. This is taken to be in the Donda gauge, so the polarization tensor dotted into the null vector, the null momentum vector k vanishes. Okay, so this is my basis of spin 1 and spin 2 wave functions in the momentum basis or the plane wave basis. And now in order to construct a new basis of wave functions where conformal properties become manifest, this is obtained by the so-called Melon Transform. What this does is it integrates from 0 to infinity over the energy omega with this particular weight factor omega to the delta -1. So starting from momentum eigenstate e to the I k dot x, performing such a Melon transform, such an integral transform, I will obtain now a boost eigenstate, which is given by 1 over q dot x, where q is this vector in which direction the particles are pointed towards the celestial sphere. So this product here to the power delta, and then there's a normalization factor that depends on delta. And I will denote these new wave functions by phi delta. So what happened here is we have the labels, which were the momenta, the energy, the helicities. They now turned into just the points on the celestial sphere, given by z and z bar. The spin j, which is identified with the helicity. And I introduced via this Melon transform this parameter delta. So this is for scalar wave functions. Now I can add the respective polarization vectors or tensors in order to get spin 1 and spin 2 wave functions in this new basis. And those I will denote by V. So those V's are the spin 1 and the spin 2 Melon transforms of plane waves. Now we, in the momentum basis, we have a basis of finite energy wave functions given by these plane waves, which are delta function normalizable. And what this implies, the condition that we have a delta function normalizable basis, what this implies after doing this Melon transform, is that we get a basis of wave functions, but this parameter delta has to be restricted to lie on the so-called principal continuous series of the Lorentz group, which means that its real part is 1 and its imaginary part is any real number. So this is a constraint on the delta. And then we have sort of state operator correspondence because we have these masses, particles, and spacetime which carry these labels. So here I have just replaced the momentum vector by omega z and z bar and at the helicity. And after a Melon transform, we get operators inserted on the celestial sphere, which I denote by O delta j. Okay, so we go from one basis of wave functions to another basis of wave functions. But what changes here is that while in the momentum basis we have manifest translation symmetry, now in this new basis, translation symmetry is obscured. On the other hand, we now have manifest conformal symmetry, which was obscured in the plane wave basis. So we have now two bases of wave functions which are useful for studying different aspects of scattering amplitudes because they make different symmetries manifest. So let me show this a bit more explicitly. Under an SL2C Lorentz transformation, which on the celestial sphere means that we have to do this Möbius transformation, these wave functions phi delta transform in the following way. So here we have the Lorentz transformation of the spacetime vectors, and then the Möbius transformation of the z and z bar coordinates on which this wave function phi delta depends. And as you can see, this wave function phi delta transforms in a way so that we can understand it as a conformal primary that has a conformal dimension delta given by this principal series value and spin 0. So now this parameter delta can be identified with the conformal dimension under the 2D global conformal group. For spin 1, it turns out that these wave functions that introduce the V's, the Melon transform of the plane waves, do not quite transform as conformal primaries, but only if we add a pure gauge piece. So once we have done that, once we have added the appropriate pure gauge piece, we can construct spin 1 wave functions, which again transform as conformal primaries, but now with spin 1. And similarly for spin 2, we have to add to this Melon transform spin 2 wave functions a pure diff, and then we also get the proper transformation properties under the 2D global conformal group. Now, these terms marked in blue, the pure gauge and the pure diff pieces, are very important if we want to connect these wave functions to the generators of the asymptotic symmetries of asymptotically flat space. I will not talk too much about that because that will be the topic of Laura's talk, but let me just give a little sneak peek here. So I said that finite energy plane waves impose that in the new basis, these conformal dimensions have to lie in the principal continuous series. So this means delta is 1 plus I times some real number. On the other hand, there are also zero modes in the plane wave basis. And the features of these zero modes in scattering amplitudes turn into features in the new amplitudes that we get with this new conformal basis. But those happen at values of delta that are not on the principal series. So those are at real and real values of the conformal dimension. And one can relate these two sets of wave functions with a real conformal dimension, or a more general, you can also think of complex conformal dimension, but ones that don't lie on the principal series. You can understand a way to go from one to the other via certain contour deformation. But I will not talk more about that. That's just a side remark. So the sneak peek is that when delta is chosen to take certain values, certain real values, these zero modes will become related to generators of asymptotic symmetries. So for delta equals to 1, we have spin 1 and spin 2 wave functions, which will turn out to be related to large U1 gauge symmetry and to BMS supertranslation symmetry. And I'm mentioning this here because the associated soft charges, which come from the soft photon current and the BMS supertranslation current, will show up a little later. But there is much more here. In particular, in a CFD, we expect to find a stress tensor. And there's also the question of whether the BMS group gets extended to include also super rotations from this celestial point of view, and that will be in Laura's talk. Is there any question on the conformal basis before I move on to celestial amplitudes?
May I ask a question? It's Marius. Hi, Andrea. So yes, I come back to the previous question that was asked about the time, you know?
Yeah. One or two more slides, because the celestial amplitudes will come up in a.
All right. I'll wait then.
Yeah. Any other question on the basis? So one thing is that it's of course a bit unfamiliar to have the conformal dimension to be complex and restricted to the principal continuous series, because this is not something that we have in the usual vanilla CFTs in ADS CFT. But that's what it is here.
May I ask one question?
Yes.
In the Melon transformation that you showed us 3-4 transparencies before, omega is the zeroth component of the 4 vector K. Okay, that's it.
Yeah, so I just for parameterize, I trade the K's all here by this null vector Q, and then I integrate over omega.
Okay, I missed that. Thank you.
Yeah, thanks.
Just a question about this continuous series that appears. Is this related to maybe some unitary requirement?
Good. So what we need here is unitary in the four-dimensional theory, right? So when we have complex dimensions in CFTs, sometimes some in the CFTs are not unitary. What is important here is the 4D unitarity. And the condition of having finite energy wave functions just turns into this condition on delta. It would be interesting to maybe recover this complex conformal dimension from some, I don't know, higher dimensional CFT, or have it as a result of some more vanilla CFT. But just from this point, relating asymptotic states with finite energy in 4 dimensions to asymptotic states in 4 dimensions that have conformal properties, this is what comes out.
Yeah, no, more precisely, I was wondering whether the fact that you work with the continuous series, is it because it has the property of being unitary representations as opposed to the finite dimensional ones? I was wondering whether that plays a role or not so much.
So the properties of unitarity and all these other things that we study in CFT in order to bootstrap and stuff has not been fully studied yet. So I'm sure there are probably very interesting things to uncover there, and the principal series probably plays a role. But I don't have too much to say about this. Here it just follows from the fact that you require this basis of new wave functions to be delta function normalizable, so you compute inner products here, and these inner products only converge when delta takes this value. So that's how this arises. But there is perhaps some more a different way of explaining how it shows up, which may well be related to what you're saying, but I don't know.
Yeah, Andrea, just a quick comment. So you mentioned that we are not so used to have principal continuous series in CFTs, but I mean, is this related to if you look into string theory in ADS3, for example?
Mm-hmm.
You have these two series, and then you have the discrete series that correspond to bound states, and then you have the principal series that correspond to scattering states. So isn't it natural in some way that you find principal continuous series for scattering amplitudes, or?
I guess it depends on what aspect of CFT you've worked on before, if it's natural or not. Here I just mean that in the vanilla ADS CFT about the boundary relations and so on, the primaries that show up have usually real dimension, and then in order to there you can expand your conformal blocks on the principal series where you have orthonormality, so you have a powerful computational tool. Tool there, but there the principal series is more sort of a computational tool, and the conformal blocks, the physical dimensions are real, while here the physical dimensions seem to be complex. It's just that it's a slightly different situation.
Okay.
May I have one more?
Yes.
Is delta also expressed in terms of the case?
Delta?
Yes.
No, delta is just a label. So the K is omega.
I'm counting numbers. For instance, K mu has four components. And in the conformal basis, I have Z bar, that's 2, plus omega 3. So I'm missing 1, it seems.
So here I have Z bar omega. I also have the helicity label, and here I have Z bar, so that's the same. And then instead of omega, I have delta, and L is identified with J. So here, I mean, yes. So the Q is just given by given in terms of Z bar, and then I have the scale omega. So there are 3, and then I have the helicity.
Where's the fourth one?
We have you have the 3 vector determines labels the state and the helicity.
Okay, thank you.
Okay, so yeah, so that matches. So omega ZZ bar and L goes to delta ZZ bar and J. Because I have not lost anything in doing this Melon transform, I just replaced omega by delta in some sense. And the question about the U integral is also sort of related to this transform here, this integration over all energies. But let's maybe look at celestial amplitudes. Maybe that becomes clearer. So now we have replaced individual wave functions from the plane wave basis to the conformal primary basis by doing this Melon transform. Now let's do this for all the asymptotic states in a scattering amplitude. So let's imagine an endpoint scattering amplitude, which is described by some function multiplying this 4-dimensional energy momentum conserving delta function. Now I do a Melon transform on all the n external states, and then I arrive at a new amplitude, which I denote by A tilde, where now the helicity labels are replaced by the spin labels, and omegas are replaced by the deltas. And it turns out that these new amplitudes take the form of 2-dimensional correlators. Now let's study a bit the properties of this. So if you do a conformal, if you look at how these new amplitudes behave under SL2Z Lorentz transformations, so on all the ZJs and Z bar Js, you do now this Möbius transformation, you will find this expression, which says that these new amplitudes, which are called celestial amplitude, are indeed 2-dimensional conformal correlation functions. And the objects involved here, which correspond to the original external parties that you inserted on the celestial sphere, carry conformal dimensions on the principal continuous series and the spins that are identified with the helicities. Now let me give some examples of these amplitudes. So in general, once again, so we have n Melon transforms. We have this 4-dimensional energy momentum conserving delta function. I will denote by Zij the differences of points on the celestial sphere, and instead of the conformal dimension delta and the spin J, I will also be using the weights H and H bar. Now, let's, as the easiest example, look at 3-point amplitudes. Let's take 2 of the particles incoming and another outgoing, and let's look at the simplest cases in gauge theory, which are the MHV3 gluon amplitude and the MHV3 graviton amplitude. And these stripped wave functions that multiply the delta function for energy momentum conservation take this form in terms of the frequencies omega and the differences of points in the celestial sphere Zij. So I could have written this in terms of the momenta, but I replaced the momenta by the omegas and this null vector q, and this null vector q just depends on the z's. So this is what you get. And now if you do a Melon transform on the 3 external particles in each of those cases, this is what we get. So this looks like some horrible expressions that we obtained after doing 3 Melon transforms and using up the energy momentum conserving delta function. But you notice that what I've written down in black here looks exactly like the expression for a 3-point correlator in a CFD. And the H's that I've written up there can be read off to be related to the conformal dimensions delta, or this imaginary part of the conformal dimension, which I called lambda. And this is the case for both Yang-Mills theory and the gravity 3-point amplitudes. Now, what's less familiar is what I've written in color. So from the energy momentum conserving delta function, I have remaining delta functions given here in blue, which constrain the difference of points of either the z or z bar coordinates. That depends on which helicity I've chosen for the particles, which is denoted by this minus minus plus here. And then in red, we have a remaining Melon integral over, in this case, the third energy, which in the case of Yang-Mills theory is marginally convergent. And we can interpret it as a delta function in the sum of the lambda j's. So this is a representation for the Dirac delta function in the sum of the lambda j's. But for gravity, this Melon integral is divergent because it lacks this -1 up there. Okay. Then for 4-point amplitudes, it turns out that the 4-point amplitudes after Melon transform can be written as some function of the cross ratios CZ bar, which are given by these ratios of the differences of points, and a universal prefactor, which is given by the Zij's and the Z bar J's to the power of the conformal weights. And by H and H bar, without indices, I denote the sum over all the HJs and H bar J's. So let's look at the MHV for gluing amplitude and the for graviton amplitude, which take this expression in the omegas and the Zij's. Now we do 4 Melon transforms, and then we find that this function here, this function f of the z's, takes this form. The stuff in black is what you would usually expect in CFD. It's just a function of the cross ratios to some power. But then again in blue, we have a remnant from the 4-dimensional energy momentum conserving delta function. And in this case, it constrains the cross ratios z to be real. So z minus z bar is constrained to vanish. And then, okay, as before, we have some extra step function that constrain the range. And then again, we have some leftover Melon integral in red, which in the case of Yang-Mills theory is again marginally convergent, but in the case of gravity is now even more divergent as before.
You have a question, Susheta?
Yes.
Hi, I was wondering that for MHV amplitudes, the double copy structure is usually relevant. I mean, already in the usual way of writing the amplitudes, you can see the double copy structure, but when you go to this conformal representation, is it correct to say that it somehow becomes obscure? Yes, very good. So, and I will hopefully have time to talk about this at the end. Okay, one point to make. So if you notice this 3-point amplitude, Yang-Mills squares into the gravity 3-point amplitude here. While on the celestial side, there doesn't seem to be any obvious square. And moreover, we have all these delta functions and these integrals flying around. So it's not clear how there could be a double copy here. For the 4-point amplitudes, there's again a relation between Yang-Mills and gravity. It's less obvious, but there are essentially 2 terms where you square 2 Yang-Mills 4-point amplitudes. So there's a well-defined double copy prescription for going from 4-point Yang-Mills to 4-point gravity for the stripped case, as I've written here. And then at least here you can see some kind of squaring going on, but again you have the stuff in color. And
so as you're very correctly saying, the double copy structure is obscured, and the reason is that usually when we talk about the squaring of Yang-Mills into gravity, we very much use energy momentum conservation. And whenever we have momenta flying around in the detailed expression of the amplitudes, we can replace them via this energy momentum conserving delta function. So we can replace any individual k by all the other k's, which we cannot do once we have Melon transform the amplitudes and are in the conformal basis. So this is obscured because translation symmetry is obscured. But I will tell you later, hopefully, how there is a double copy for the celestial amplitudes, and it requires going away from explicit momenta to operators. So I will come back to that later on.
Okay, thank you very much.
Thanks for the question. Okay, so I've already said that we have the amplitudes, the celestial amplitudes have 2D global conformal transformation properties. Now we can also write the Lorentz generators in terms of derivatives with respect to the angles and the conformal weights. And then the statement is that when you sum over all the action of these generators on the amplitudes, you get 0. Now, another thing, and this relates precisely to what has just been asked, what about translation symmetry, since the original amplitudes were translation invariant? Now, the translation generator, it takes the form of an exponential operator, of a differential operator with respect to the weights. We still have translation symmetry in this form, so S denotes whether you have an incoming or an outgoing particle. And then this operator acts on the amplitude. And so once you sum over all of the actions of this operator, you get indeed translation invariance. But for the amplitudes themselves, you cannot use the fact that the sum of all the momenta k sum up to 0, because you have integrated off the energy omega inside this, this momenta. And so we will have to do a bit more work to see how in particular, the double copy relation arises in celestial amplitudes. Okay, so, but keep this in mind. So we have this translation generator, which takes the form of this differential operator. And this will also play a role for loop amplitudes, which I will now get to. So there's not too much work on quantum effects yet, because it's difficult. I will just give us a sneak peek of what is going on there in the context of planar n equals 4 super Yang-Mills, because the reason is that the 4 gluon amplitudes in n equals 4 super Yang-Mills in the planar sector is UV finite and is known to all orders in the loop expansion. And a good way to regularize the IR divergences is to use dimensional regularization. In particular, since we're doing Melon transforms of all the external particles, it's good if we can keep the external particle momentum polarization vectors in 4 dimensions, but then we allow the internal momenta in the loops to live in d equals 4 minus 2 epsilon dimensions. So what happens for the 4 gluon amplitude in this theory is that we can actually write the all loop amplitude as the 3-level amplitude multiplied by some scalar factor. And we can also write this as contribution of all the different loop level amplitudes that then combine to the all loop result in this theory. And this scalar factor, that is the thing that contains all the difficulties. So the scalar factor depends on the Mandelstam invariants S and T, which are related to the momenta Ki in this way, and also on the dimensional regulator. And this little a that I wrote here is the top coupling. Now, for the one loop contribution to this amplitude, the scalar factor takes the form of a scalar box integral, where we integrate over the d-dimensional internal momenta. And this integral can actually be solved in terms of hypergeometric functions. It can be written in a form that there is a function that's that contains IR divergences. So that's denoted by this epsilon, which is the dimensional regulator that I introduced before in the dimensional regularization scheme. And then there's a cross ratio R which is given by the ratios of these Mandelstam variables, which is a slightly different cross ratio than I've chosen before in the tree level amplitudes, but that doesn't really matter. So this scalar factor can be written as this expression f. And then the important thing is that you have 1 over the Mandelstam variable to the epsilon. And these Mandelstam variable T and S, they contain powers of the energy. And so when we try to compute the celestial one loop amplitude, we will have an additional contribution from the energy that comes with the power epsilon. So let me just remind you, before I showed you that the 4-point celestial tree level amplitudes, Melon transform to give this expression f in terms of the cross ratios, which now are called R and R bar, and then this universal prefactor. And they're given by, I have already written this before, but I've written it now again with the coupling constants reinstated, and I have written it in terms of the z's instead of the lambdas and the h bars, lambdas and the HH bars. And then this capital I of lambda is just the integral, the remaining Mellin integral that I wrote before, which I told you can be is marginally conversion and can be written as a delta function over the sum of all the lambdas. Now this is the tree level result. The extra power of energy with power epsilon that comes in here will change the value of the Melon transform. And what it does is essentially shifts the conformal dimension. So it shifts this imaginary part of the conformal dimension called lambda by some value that depends on epsilon. And we also have this infrared divergent function that differs from the tree level result. So there's the tree level result and the one loop result, and the one loop result has this integral that was marginal conversion for tree level, but now has an argument shifted. And this shift in this argument can actually be understood as the action of a differential operator acting on the tree level Melon result. And this means that we can, or it suggests that we can express loop level amplitudes in terms of tree level amplitudes where we have some differential operators acting on them. And this is indeed the case. So before I wrote the one loop result with a scalar factor on the tree level result, and now I put tildes on there and made this loop scalar factor m calligraphic, because now it's an operator. So you can show that you can compute the celestial tree level amplitude and then act with a loop operator curly m here on it to get the celestial one loop amplitude. And this celestial one loop factor, which previously was obtained by solving the scalar box integral, now is given by an operator. And this operator that I've written in red here is precisely related to the translation generator that I've introduced you a few slides earlier. So I think there I've written e to the d by dh and d by dh bar, but I can also write this in terms of the lambdas or the deltas. And translation symmetry was obtained by taking this operator and having it act on each of the particles in the amplitude and then summing over all of them. While here for the loop amplitude, we have a product of this operator acting on each of the particles simultaneously. So this is all that I wanted to say about loop amplitudes. It seems that at least in the case of n equals 4 super Yang-Mills, we can write tree level amplitudes with operators acting on them, and that gives us celestial loop amplitudes. And in the case of n equals 4 super Yang-Mills, it's also nice that we can extend this to all loops. So the all loop result also takes this, we have this factorized form. Again, we can write this scalar loop factor as some function of the cross ratios and some function that's just dependent on the, some function of the Mandelstam S and T and a function on the cross ratios. But maybe let me skip to the punchline, which is that we can express the celestial all loop result by some operator acting on the celestial tree level result. And that's all that I had to say about loop amplitudes. I will go back to tree level, but let me maybe ask if there is a question at this point.
Well, maybe I do have a question. So but what is the structure of this loop operator? So is there a clear systematic, so you have to compute them loop by loop? So for instance, the differential operator is always the same, and it's only the prefactor that changes, so the structure is completely different at each level.
So I cannot give you an answer, a general answer, only for n equals 4 super Young mills,
Yes.
or 4-point amplitudes. And in this case, so the one loop operator, this curly m here, was given by this infrared divergent function, and then this operator p to the power epsilon, and this operator had this dimension shifting exponential operator in here, and then a prefactor that, well, let me not talk about this, but this is the structure for the one loop result. Yes. And so this had just this operator to the power epsilon. Now for the L loop result, we have again the same operator, but now to the power L times epsilon.
Okay, thanks.
And this function also is, because I showed you before that there is a, or maybe here. Yes, so there is an L loop contribution, and so this F also has a 1, 2, 3, 4, and etc. loop contribution. But these functions are known at least to a certain loop level.
Okay, thanks. But the differential operator is always the same with a different power.
Here, in this case, it is always the same, but with a different power. Yes, okay. But this function is a different function.
Okay, thanks.
Yeah, so it's a nice feature that in n equals 4, this happens in such a nice way that you can write the L loop amplitude, and then you can sum up all these contributions and you get the L loop result. I don't know what the statement will be for other loop amplitudes, for other theories, for higher points and so on and so forth. But I think what some preliminary results have revealed is that the fact that you have these dimension shifting operators, that seems to be there. And it's here, it really just follows from the fact that you have this additional factor multiplying the tree-level amplitude, which has some powers of energy to the, which comes with energy to some power in epsilon. And then you integrate over, and then you get this shift, and this shift can be incorporated by this exponential operators that shift the dimension. Yeah. So maybe this was a bit fast, or maybe a bit detailed, but so this is just a sneak peek of what could happen, maybe more generally in celestial loop amplitudes. But now we'll return to tree level, and we'll discuss some features of tree level amplitudes. So one is the fact that I said we have finite energy wave functions be mapped to wave functions living on the principal continuous series. But what about zero energy wave functions? In particular, in scattering amplitudes, we have the energetically soft limit, which takes the energy to 0, and that gives rise to universal factorization theorems of amplitudes. And by doing this Melon transform in the energy, which makes us integrate from 0 to infinity over all the energies, this limit seems to be lost. But surely, if you have a universal feature of an amplitude, it will not be lost when you do a change of basis. So what we proposed instead of the energetically soft limit in the plane wave or momentum basis is in this new conformal basis to take a conformally soft limit, which takes the conformal weights to 0. Now the story is actually more general, which already hinted at before, which is that in the energetically soft expansion in 1 over omega of the amplitudes, we get a structure of residues, which seem to agree with the poles in celestial amplitudes when you take the conformal dimension to have certain real values. So when you do an energetically soft expansion of an amplitude, the first thing that you get is you get a 1 over omega pole, which comes with a universal factor in Yang-Mills theory and gravity, say. Then there's also an order 1 in the energy term, which has a universal soft factor in gravity. And then there's another term which comes at order omega, which is also a soft factor in conformal soft factorization of gravitational amplitudes. And these seem to agree with taking, or at least the fact that the amplitudes factorize, seem to agree with taking certain limits of the conformal dimension for the celestial amplitudes. So let me show this for this leading soft factorization for Young-Mills and gravity. So what we do is we look at an endpoint amplitude in Young-Mills theory, where we take the energy of an external massless particle to 0. This results in a factorization which gives an amplitude that has one less particle. So it's an amplitude without the energetically soft particle, and it's multiplied by a soft pole. And this soft pole comes with a universal factor, and this universal factor can either be written in terms of the polarization vectors and the momenta, or I can write them in terms of the differences of positions on the celestial sphere, namely these angles. And then we have this very universal factor for an endpoint amplitude in Young-Mills theory. Now this translates in the new conformal basis to taking a certain limit of the conformal dimension. And what this means is that in the celestial amplitude, where we have certain operators inserted on the celestial sphere, we take one of these operators to have a certain conformal dimension. So for this case, we take the conformal dimension to be 1, or the weight, which is equivalent to taking the weight to 0. And then we get a celestial amplitude without this conformally soft operator, but we get a conformally soft factor, which I denote by as tilde here, which agrees precisely with the momentum space soft factor. So after this change of basis, after integrating over all the energies, the energetically soft factorization with this universal soft factor turns into a conformal soft factorization with precisely the same conformally soft factor. So that's nice because it means that universal factorization properties survive in the conformal basis. Similar story for gravity, a bit more complicated. Again, we have a factorization of the n graviton amplitude, but now the soft factor and the momentum basis contains explicit powers of the energy, which means that after you Melon transform into the conformal basis, this extra powers of energy will mean that in addition to taking the conformal dimension of one of the operators to be 1, and each of the other operators has to have a shifted conformal dimension, because you integrate over the energy and you have extra powers of certain energies, which means that the exponent gets shifted, and so you can incorporate this by shifting the conformal dimension delta. At the end of the day, the function that just depends on the positions, the angles on the celestial sphere, is precisely the same in the conformal basis and in the momentum basis. So once again, we see that this universal feature of factorization remains present in the conformal basis, but it shows up in a different guise. Now in logos, yes.
10 minutes left, just to mention.
Yes. So how many?
10.
Okay, great. So in logos basis, in logos talk, you will see that these conformal primary wave functions, which have the pure gauge and the pure diff pieces added, will give rise to conserved currents. And for gauge theory, this will be the soft photon or soft gluon current. And for gravity, it will be the BMS super translation current. And you can relate the soft factorization theorems to asymptotic symmetries, as we have already heard in several talks yesterday. And what happens here is that when you insert these conserved currents into the amplitude, it gives rise to certain OPE with some operators in these amplitudes, which in the case of gravity come with an extra power of the energy. And so you can explain this feature that I showed you before in the form of this OPE, where in the momentum basis we have an extra power of omega in the OPE, while when we integrate over all the energies, this turns into a shift of the conformal dimension of the operator. So this sort of explains this more curious feature that you have celestial endpoint amplitudes in the conformal soft limit related to celestial lower point amplitudes, where the dimension of the remaining particles are shifted. Okay, so very good. So we have, instead of energetic soft factorization, conformally soft factorization. And this is related to the insertion of the conserved currents that are related to the asymptotic symmetries in the respective theories. Okay, any question on conformally soft factorization? Okay, if not, then let me briefly mention celestial OPEs. So instead of taking the energetically soft limit of amplitudes, you can take the collinear limit of amplitudes, which means that momenta become parallel, or replacing the momenta by the omegas and the z's, it means that zi goes to zj, if we take the limit that the ith and the jth particle becomes parallel. So what that means is, if you take this limit in an amplitude, you can write it as a certain function called a split function, acting on the amplitude, where we have the two particles that become parallel, have its momenta replaced by p, and the sum of the energy is replaced by omega p. Now, when you do a Melon transform of this collinear limit for these particles, what you will find is that you can extract from the collinear limit of this Melon transformed expression how two operators come close on the celestial sphere, because this collinear limit is nothing but an OPE limit when translated into the celestial sphere. So, for example, for positive Phillips gravitons, the split function takes this particular form. You plug it into the Melon integral, and then you will find that two gravitons of positive helicity with dimension delta I and delta J, located on points Zi and Zj, in the limit where these points come close, is given by some function of the Zi J's and Z bar Ij's, a graviton that's inserted on the point Zj. And then after doing this Melon integrals, you will find that there is a function in the conformal dimensions, which in this case is given by the Euler beta function. So it's a ratio of gamma functions that depend on the deltas. So from the collinear limit of these amplitudes, you get a prediction for the OPE coefficient, which is dependent on the conformal dimensions. And you get the constraint that the operator that arises in this OPE has conformal dimension given by the sum of the conformal dimension of the individual gravitons. There's another way you can understand the OPE, and there will be much more in Angelo's talk about collinear limits. So let me not say any more on that. There's another way to understand the OPE which is from asymptotic symmetry point of view, where you look at how the OPE arises from 3-point vertices of say gravitons and gluons, where you count the amount of derivatives that arise in the 3-point vertices, and then you get some general expression for the OPE, which comes with some function that you have to determine. And to determine this function, you make use of the asymptotic symmetries. So one thing is that the translation generator that I've shown you before shifts the conformal dimension of a graviton. Then if you look at the leading conformally solved graviton that I just discussed, it gives you a constraint on the normalization of this function that appears in the OPE. And then there's a more complicated constraint that arises from the sub-leading conformally solved graviton theorem, which arises when delta goes to -1 and which I didn't discuss before. So for the positive Phillips gravitons, what this means is that you can determine the function that arises in this OPE, and this function agrees precisely with the one that you get from the collinear limit. So this was maybe a bit fast, and there's a lot of detail that one can give, but this is just to give you sort of a picture of how one can determine OPEs in the celestial CFT. Now, I think I have maybe 5 minutes or less than 5 minutes left. So let me just mention what I hinted upon before, which is a double copy for the celestial amplitudes. So what's the double copy? The slogan is gravity is Yang-Mills squared. What this means more precise in equations is that if we start from an n gluon amplitude in Yang-Mills theory, which is given by this four-dimensional energy momentum conserving delta function, and then a sum over graphs where we have propagators hidden in this pi in the denominator. We have color factors given in blue, and we have kinematic factors in red, which depend, which are polynomials of the momenta and the polarization vectors. And these color factors, they satisfy a Lie algebra Jacobi identity given here in blue. At tree level, we can always find kinematic numerators n that satisfy a similar identity relating the ST and the U channels of the amplitudes. And then what the double copy then says is that if you replace the set of color factors by another set of these kinematic numerators that satisfy this identity, so you get the kinematic numerator squared, then the expression that you get, surprisingly, turns out to be exactly the n graviton amplitude. So in this way, starting from an n gluon amplitude Yang-Mills theory, you replace these color factors by kinematic numerators, so you have kinematic numerator squared. This gives precisely a gravity amplitude. And as I hinted before, when the question arose, how does this work when we change bases and when we give up this manifest momentum conservation? So it's very heavily used that you can replace any momentum by the sum of all the other momentas in the amplitude, because you have a manifest translation symmetry in the basis where you use plane waves. Now, once you go to the conformal basis, translation symmetry is obscured and you don't have explicit momentum conservation anymore. But what you can do instead is you don't use the four-dimensional energy momentum conservation in performing the Melon integrals, but you leave them explicit as these space-time integrals. And when you do that, you will find that this is actually the most natural way to generalize this mysterious double copy relation to settings where you don't have explicit momentum conservation. And it has already been useful to use this procedure when studying double copy on curved backgrounds, in particular on plane wave backgrounds. So the celestial amplitudes lie somewhere in between flat space and curved space, because you have to use this, this procedure, which you need in curved space to see a double copy structure arising, but it doesn't have the complications of curved space. So it seems a very good ground to study in more detail the fundamental features of this double copy relation. And important point here is that since we're using energy momentum conservation, which can also be written as integration by parts, the important point here is that when partial derivative acts on the plane wave functions, you project out a factor of the momenta. And it's important that these momenta are spacetime independent. Let me just quickly show you how for 3-point amplitudes the double copy works when instead of using this energy momentum conserving delta function, you keep explicit the spacetime integration. So the 3-point vertices contributing to the 3-point amplitudes in Yang-Mills and gravity take this form. So there are a bunch of spacetime derivatives in here. And the wave functions are just the ones that are introduced on the, I think, second or third slide, which are the plane waves with the polarization vectors and tensors. Now, when you plug them in, you get some expressions shown here in gray, but then you massage the expressions a little bit and you use integration by parts, and then you will get a simpler expression for gravity. And the simpler expression by gravity, if you look closely, is precisely the squared integrand of the Yang-Mills amplitude. And so if you strip off these factors of the plane waves, e to the I k dot x, and you look at just the integrand of these spacetime integrals, you will find that Yang-Mills integrand squares into gravity. And so this is the double copy statement for the plane waves in the plane wave basis, where you have the explicit momentum conservation replaced by leaving this integral, spacetime integral. And the statement is at the level of the spacetime integrands. I think I've run out of time, so maybe I'll just skip to the punchline. So the point is that when you replace in the 3-point amplitudes or more general n-point amplitudes, the plane wave functions by this new basis of conformal primary wave functions, the naive double copy does not work. And the reason is that the way that partial derivatives act on the plane waves is a little different when they act on these new conformal primary wave functions. So I've shown this here. So they act in a way that they again project out an expression which I call celestial momentum in analogy to how spacetime derivatives act on the plane waves. But now this spacetime, the way that these derivatives act on the conformal wave functions is that they have a spacetime dependent momenta here instead of spacetime independent momenta. And so this means that if you try to rewrite the celestial 3-point amplitudes where I've performed the Melon transform, and you try to integrate by parts the gravity expression, you will not get the square of the Young-Mills integrand. So here these are exactly similar looking to the momentum space 3-point amplitudes, but the momentum, the little momenta k are now replaced by the celestial momenta, which are space-time dependent, and so the double copy does not work in the naive way. And the reason is that when hitting the celestial momenta with space-time derivatives, they don't give 0, but they give extra factors that involve the conformal dimension. And so I'm out of time, so let me just give the proposal for how the celestial double copy is made to work, which is that whenever you have celestial momenta arising in the amplitudes, you should replace them by differential operators, which are denoted by curly k. And these differential operators are defined to act on the wave functions phi, the conformal wave functions, in the way that's given in the box here. So this is an eigenvalue equation, so you do get the celestial momenta back, which are the space-time dependent momenta here. But these operators also come with a label, so they keep track of the particles, and they give only a non-zero answer when the label of the operator is the same as the particle or the wave function. So in that sense, they're not equivalent to the usual partial derivatives acting on wave functions because they keep track of the particle label. And if you remember from before, the way that these celestial momenta were defined in terms of this null vector q and the conformal dimension shows you that the action of the celestial differential operators is precisely the same as the translation generator that I introduced to you earlier. But now it acts on the ith particle individually and not in a sum that that shows translation invariance of the amplitude. So let me just go maybe to the punchline, which is that when you introduce these differential operators, they act on wave functions. They give rise to these extra terms that come with a function of delta. But the way these derivatives act is such that they precisely cancel all the terms that were mismatching in the naive double copy for celestial amplitudes. And at the end of the day, when you replace all these momenta by differential operators, you get operator valued numerators inside the space-time integrals. And when they act on the wave functions, you get that the Young-Mills numerator operator squared gives the gravitational numerator. And so you have a double copy between celestial 3 gluon and 3 graviton amplitudes. And the same works for 4 points as well. Things are more complicated, but since I'm out of time, let me just tell you that also the 4 gluon amplitude double copies into the celestial 4 graviton amplitude, and it just happens in the way that you replace the momenta by differential operators, and then the squaring of Young-Mills to gravity happens by replacing the color factors not by numerators, but by operator valued numerators. Okay, and the last thing that I want to say is that this gives a nice way of presenting amplitudes, which is that once you go to the celestial amplitudes, you can write them as some amplitude in terms of the scalar wave functions phi. And you get Young-Mills theory, Young-Mills amplitudes, by acting with these operator valued numerators on the scalar amplitudes. Similarly, you get gravity amplitudes by acting on this scalar amplitudes with the gravitational numerator, which is Young-Mills numerator squared. And this goes to higher points as well for the 4-point amplitudes, and higher this works as well. And we can therefore start from just scalar amplitudes and recover Young-Mills and gravity by acting with these operator valued numerators. So this is a summary of all the different topics that I tried to cover. But I'm out of time, so let me just say that celestial holography is very much a developing story, and so thank you for your attention.
Thank you a lot, Andrea, for this very informative talk. So we can take a couple of questions since we have a long lunch break. We have a little shift here, but it's okay. So if you have questions for Andrea, yes, Marius?
Yes, thank you. Thank you, Andrea, for your talk. So I come back again to this issue that was raised in the very beginning, and and maybe I can say one word, and then you can comment. Of course, this is the expectation. So this program seems to me that might be somehow a sort of successful translation for the usual way of writing down amplitudes and computing amplitudes in the normal basis that we use, translating in what you have called the celestial basis. But this seems to me that it is very much conditioned by the usage of massless particles. It seems to me that if you want to introduce massive particles, you will be lacking degrees of freedom somehow. And this translates in the fact that if you really want to talk about holography, then you cannot ignore the third dimension of the boundary, which is time.
So I did not talk about the massive amplitudes, and in some sense they look a little bit more like the usual CFT correlators because they don't have these delta functions flying around. There's a couple of results where people looked at scalar 3-point amplitudes with 1 or 2 massive particles, and there you get a structure like the one written below here. So most of the work has focused on massless processes, but now in the past couple of months, spaces for massive wave functions have been constructed, and there are a few amplitudes that involve massive particles as well. Okay, maybe, yeah. So what the Melon Transform does, it takes this amplitude to something that looks as a two-dimensional correlator. That's just what you get. And the generators of the asymptotic symmetries, which I just hinted upon, but which will be discussed more in Laura's talk, they involve, as you know well, these conserved quantities at null infinity involve integrating over all of null infinity. So from minus infinity to plus infinity in the retarded time. So, and this is consistent with this basis of wave functions described at null infinity. I agree that so it does not have the flavor of ADS-CFT in the sense that we don't go from D to D minus 1. And there's surely some more to be uncovered and understood here. And hopefully there is a limit that we can actually go from ADS-CFT to flat space holography, and that should then reveal what's happening with time. But indeed, you're right. So in this program, we are replacing, so this is sort of like a bottom-up approach by starting from scattering amplitudes, doing some integral transform, and then finding something that has the structure in a 2D. And it would be very interesting to uncover if we can get this from, let's say, a 3D CFT where we do some reduction or something.
So maybe we should take other questions.
Thank you.
The one of Sucheta.
Yeah, thank you for the very nice talk. I was wondering, so for the n=4 super Yang-Mills loop amplitudes, you showed a very nice relation how those can be written in terms of the 3 amplitudes. So I was wondering that, is this somehow related to the bigger symmetries of the theory, maybe dual super conformal symmetry or something? Has this been explored?
Yeah, I think yes. Yeah, it's well, not really explored too much. I think there is probably a connection. So here, the interesting thing was, or the thing that made it possible to write this amplitude in such a simple way, is that the loop amplitude had this very simple dependence on the energy. And so with this very simple dependence on the energy, you could write this relation. I don't know if this holds more generally for other theories and more complicated loop amplitudes.
No, I mean, yeah, so in the n=4 theory itself, just yeah, this, because n=4 is very special. I don't expect it to be holding for any other theory.
Yeah, it's okay. It might whether or not the structure that you can write a tree-level amplitude, celestial tree-level amplitude with an operator acting out given loop level, it's a question of whether this is more general. It might be, at least for some theories, and I think there's upcoming work by other groups which at least find that these dimension shifting operators work there as well in other groups than in other theories than n equals 4 sub n mils. But okay, in general, it's not clear whether this factorized structure holds. Then in n equals 4 itself, this might well be related to dual conformal invariance, because it's, I mean, that's just the symmetry of the original amplitude in the plane wave basis. So the question is whether it's manifest here or whether it's showing up in a different guise, like in this, in the conformal basis, translation symmetry is not manifest, but it shows up in the way that if you take the momentum translation operator acting on the amplitude and you sum of all of them, you get 0. So it's still there, but it's not manifest. So perhaps this is the case here too.
So we have 2 extra questions. One of Fabio, then Charles. Please, Fabio.
Hi, Andrea. Thank you very much for your talk. Very interesting. So I don't know much about double copy, for example. So when you mention double copy, is valid only at the tree level or also to all loop?
There are results. So for in the usual momentum basis double copy, there are results at loop level, but I don't think it has been proven, unlike at tree level. So is the question about that in general or about the celestial?
Yeah, I mean, the other question is, what does this teach us about non-renormalization? Like the fact that gravity in 4 dimensions is non-renormalizable. So, but Young-Mills in principle it is, right? So yeah. What does it mean in this context?
So one thing that you could object to when I wrote down these celestial amplitudes is that if you remember, there were these remaining Melon integrals, which were marginally convergent in Young-Mills, but which were divergent in gravity, and more so the higher we go up in multiplicity. So you could have objected, how could you even, you know, imagine that the celestial Young-Mills squares into gravity if Young-Mills is marginally convergent and gravity isn't. But the point is that these numerators, when you have Young-Mills, they act on the scalar wave functions, it gives you this marginally convergent expression. But when you square it and have it act on the wave functions, it gives you the gravity numerator, which we know to have this divergent remaining Melon integral. So I don't know if, I don't want to say that we learned something new about the non-renormalizable of gravity, but it puts it in a different, it expresses so it puts it in an operator valued statement, which is that for Young-Mills, you get this nice marginal convergent expression, and for gravity, you can relate it to Young-Mills, but you also have to keep in mind that when you square this operator, you shift the conformal dimension in such a way that you get divergent integrals. It's a different way of encapsulating that statement.
So now, so quickly for the last question for Charles.
Hi, Andrea.
Hi.
So if I understood well, for the moment, the duality you've presented relates an S matrix in flat space to correlators on A boundary, so with in and out. Have you guys tried, or do you know of people who have tried to build to derive other kinds of duality from this duality, or other, basically a duality that would involve other quantities than the S matrix? And also, can you recover other features of holography from this duality, like reconstruction of bulk fields, or I don't know, like features that we know of in ADS?
So I'm not sure what other dualities you mean. So here, I'm not sure if duality, so it's a change of basis that relates certain observables to certain other observables. The wave functions that I've shown you are exact bulk solutions, so that those are not just boundary valued expressions. Those are real, they are bulk solutions to Maxwell and linearized Einstein equations. So I'm not sure what, so what other quantities maybe you have in mind?
I mean, I know that in ADS you have a partition function in the bulk. I know you can also derive, you can use the duality to derive other dualities, like the Ryu-Takayanagi formula, for example, is a kind of duality. I'm asking if you can deduce from this duality other relations for bulk quantities that we know of.
Yeah, so I mean, right now this is at this point it's still bottom up. What you know about amplitudes, you can try to translate into the conformal basis and see what you get there, and the features persist. And then ideally on the celestial side, ideally you would like to be able to study something on the celestial side and then infer something about the bulk. Maybe this is what you're interested in. But at this point, it's not yet clear what are the properties of this putative celestial CFT. At this point, it's trying to learn something from the amplitude. And there have been some work, and I guess you could maybe also put the celestial OP from asymptotic symmetries into that category, that tries to sort of bootstrap on the celestial side itself, and then get a prediction from that, which then can be checked against the known bulk results. But at this point, it's very much in sort of the baby stages of developing a potential holographic duality, because we don't really know yet what the full extent of this putative CFT is.
All right.
So I'm not really sure what I can.
So I think we should stop here and keep more questions for the break. We're going to shift the break, and we're going to have a 15-minute break after Celine's talk. So let's thank Andrea virtually. Well, I don't know if you can put your micro for the right. So Céline, could you?
I'll try to share my screen. Yeah, do you have it?
Yes. So yeah, perfect. Okay. We see it very well. We don't see it full screen totally, but we see it.
Okay, let me.
It's good enough.
Yeah, is it good?
Yes, perfect now.
Great. So yeah.
So you will have a 20 minutes plus 10 minutes questions.
Okay, perfect, thanks. So first I want to thank the organizer for this very nice, interesting workshop. And today I will talk about charge in three-dimensional Bondi gauge. And it's a work that I'm doing with Romain Ruzziconi, that is also in TU Vienna, and it will appear early December. So in this talk, what I will do, I will consider asymptotically locally flat ADS space-time in three-dimension Bondi gauge. So why? First of all, as Daniel has mentioned also in his talk, 3D is simple yet non-trivial. You have black hole solution, even though you don't have local degrees of freedom. And we want to study that case because we want to apply these boundary degrees of freedom program that I will present you in a minute on asymptotic boundaries. And the other big motivation was to study Bondi gauge without fixing the boundary metric, except assuming the conformal compactification. Also, I will talk a bit more in the motivation. So this project takes place in the big picture of studying the gravitational spacetime with boundaries. And so, as we have been discussing for 2 days, here, you know that you have, for example, the asymptotic boundaries, Cry plus. You have also another type of boundary that are really interesting to study is the causal boundary, for example, the horizon of a black hole. And when you would like to do that, I mean, you have, as we all know, the holographic dualities that takes place on the boundary of the spacetime. If you want to address the question of black hole microstates, you might wonder where this microstate takes place, maybe on the horizon of the black hole, how to describe them, and so on and so forth. You have also, like, as Gela was mentioning yesterday, all this discussion about what is the corner macrostate corner algebra that you want to put. So also you put surfaces in your spacetime in that case as well. You also have, for example, for asymptotic boundaries, you have all the observable you would like to measure, for example, the gravitational memories effect. And so for and so forth. So what I want to mention is that because you put a boundary, it means that you break the full diffeomorphism invariance of your theory, as Mark and Daniel were mentioning yesterday. And because you break this full diffeomorphism invariance, there is more degrees of freedom that I will refer to them as boundary or soft degrees of freedom. And they are just there because you put a boundary, because you break this symmetry. And if you, as Mark was saying, if you want to restore the full diffeomorphism invariance, you had to add this extra mode, the H mode. But here I will take the point of view of you breaking the full diffeomorphism invariance, and so you have these boundary degrees of freedom. And those are of different nature with respect to the local propagating Burl hard physical degrees of freedom. People have been using all this word in the literature. And those are degrees of freedom that you cannot erase by a symmetry. They are there all the time, and they are there in your system. And for example, the graviton, the propagating graviton is an example of these physical degrees of freedom. Gravitational waves in 4 dimensions as well. So the first big motivation of this project was the Boundary Degrees of Freedom program. And that's a program that we have been dedicating ourselves for since 1 year with my collaborators. Some of them are the audience, so you can also talk to them if you want. So what is our goal in that program is to do a systematic treatment of the boundary degrees of freedom and their interaction with the bulk degrees of freedom. As I was telling you, there is these boundary degrees of freedom, but what are the maximum number of them that you can switch on? How to realize a setup when you switch on this maximal number? So in one of these papers that I cite here, we have been argued that you're expecting d boundary degrees of freedom by a counting argument for a d-dimensional gravity system. And we have an explicit example. We have shown that we can indeed realize this maximum number of degrees of freedom for a generic surface in 3D Einstein gravity and for 2D dilatant gravity. Here, I want to stress that these boundary degrees of freedom, they are codimension 1 function. So if you fix your boundary to some radial coordinate, it means that it will depend on the time and the angle that you are left with. So yeah, that's an important technical precision. And another question in this program that we have is like, how these boundary degrees of freedom, how they interact with the bulk degrees of freedom. And we came up with this conjecture that stating that if you have no genuine flux through the surface you are considering, so it means no local degrees of freedom or no gravitational wave through your surface, it means that it exists always slicing of your phase space such that the charge will be integrable. What I mean by choosing a certain slicing of the phase space, I mean a field redefinition of your symmetry parameter that will render the charge integrable. And we will see one example as well today. I'm spoiling you the end of the talk. And we have mentioned yesterday this field redefinition in Luca's talk and Daniel also. And it has been to think about the fact that the symmetry generator, you can change the state dependent, has been very powerful in the last couple of years when we were realizing that, as Daniel was saying, different symmetries, group of symmetry can be realized to some boundary condition depending on the field definition, redefinition of your parameter. And that conjecture we have shown on particular examples, so the topological theory I was mentioning, but for a generic surface. And also we have work in progress. We have already that result that, for example, for 4D dimensional spacetime, when you have gravitational wave through your surface, it is impossible to find a base where the charges are integrable. And we have also working, as Shane was mentioning yesterday in the chat, that we are working on the topological massive gravity right now, where also you have some degrees of freedom. So you're expecting also to have some situation where the charges are not integrable because of these local degrees of freedom. And so the question was like, what's happening for asymptotic boundary? because there is some quantity that diverges, and so we wanted to see if the conjecture will work also in that case, even though we expect it is the case, but I think it's a non-trivial check of this conjecture. And for that, we have chosen to work in the Bondi gauge. So Bondi gauge has been studied in the literature for a couple of years now. So you have the first couple of work on the Bondi gauge, Bondi, Van der Waals, Metzner stacks, and after more recently with, I mean, okay, the list of people are there. And why this Bondi gauge is important because it is adapted to study asymptotically flat spacetime. And in particular, it's practical to study phenomena with gravitational waves because Bondi gauge is based on a null direction along when you to go to null infinity. And also another feature that is interesting that that Adrien has mentioned yesterday also in his talk is that you can study ADS spacetime in Bondi gauge. Nothing prevents you to do that, but it's very nice because you can take the flat limit in that case, while it's not the case for Pfefferman-Graham, for example. So it's interesting to see how result in ADS can be transported or not to the null cases. And what we will do here is that we will relax the assumption on the boundary metric. So we just assume the conformal compactification and that's it. And because it's at infinity, you have quantity that diverges, as we have seen also in the Hamiltonian formalism yesterday. And we have to renormalize our quantity. And so here, one of the other output is this renormalization from any boundary metric for Bondi gauge in 3 dimensions. So very short table of contents. I will first define precisely what is the Bondi gauge in 3 dimensions. I will show you that we managed to renormalize the charge, the quantity. And also I will talk about the integrability and the charge algebra we obtain. Oh, let me know if you have any question. I don't know if in that stage there is already a question or no. Okay, so Bondi gauge. So first you define U and you call U your retarded time and you choose U such that U equal constant is null. So that's the red line I drew here. You choose R, your radial directions, that is varying along each null ray, U equal constant. And here I depicted the R equal constant surfaces. And so your boundary will be at R equal infinity. And you also introduce this phi 2 pi periodic direction that is constant along each ray. And you assume conformal compactification. In ADS, you can also use this set of coordinates on ADS spacetime, and there you will describe the future time-like boundary. So the metric can be written in that form. So the fact that G phi 5 is just R squared E to var phi, this is what you ask to have a conformal compactification. And all these 3 functions here, V, beta, and phi, var phi, are completely arbitrary function of U and R. So I'm just translating this requirement in the metric. And so as I was saying, the boundary at R to infinity, and we can describe future null infinity and time-like boundary. Very good. The solution space for that setup has been worked out recently in a paper by Charles, Luca, Marius, and Romain. And the result is the following. So if you impose the equation of motion on the line element that I gave to you, you get this following 3 constraints. So you see that 3 equations. So your beta here will just be a function of U and phi. U is defined as such. And you have also 2 evolution equations, so 2 constraint equations. So this function here, the M and N, their evolution will be constrained. So here the dot 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 represent function of beta 0, U0, and V. I didn't write N because it was a bit lengthy. So the solution space you get in that setup is you have 5 functions of 2 variables, so codimension 1 function, and also 2 constraints. And so, as I was already mentioning, beta 0, u0, and phi characterize the induced boundary metric gamma AB. So if you take R to infinity, okay, if you rescale by R squared and you take R to infinity, that's what you get, this gamma AB. And I want to say that you can define gamma AB for any R equal constants on the foliation by R. And you just take the normal vector and you compute the induced boundary metric, the induced metric on that foliation. And also the 2 function m and n, as you will see, will be related to the, they are encoding the bulk information. And what I mean by that is they will encode the mass and the angular momentum if you put, for example, the BTZ black hole on your, on this setup. But we will see that when we were computing, when we will compute the charge. Okay, so that's the solution space. We have 5 functions.
Question?
So now, as Daniel was very nicely reviewing yesterday, we want to consider the asymptotic symmetry. So we want to look for the vector such that they preserve the Bondi gauge. And for if you do the computation, you realize that the vector is depends on 3 arbitrary functions. And because we have not fixed the boundary metric, we have 3 arbitrary codimension 1 function. So our f will be the translation, I mean the super translation, or here it depends as well of u, but if you take the 0 mode, will be the translation along the u direction. Phi will be the rotation, y will be the rotation along the phi direction, and omega will be the Weyl transformation, and you can see it from the transformation law of your conformal factor y phi, for example. I choose to not display all the transformation law because it was lengthy and I think it doesn't bring anything, but you can look it up in the paper. So now what you want to consider is the algebra, and you have to consider this adjust or modified bracket as because it's the one that will take place when you look at the charge algebra later on. And so you have to take into account the fact that your psi are state dependent, as we clearly see it here. So if you can compute this algebra, what you get, if you take just to understand what is this algebra, we take that now f, y, and omega are state independent, meaning that the delta is 0. And what you find is just that the Weyl transformation commute among themselves, and f and y generated the algebra of the diffeomorphism of the cylinder spanned by the u direction and the phi direction. So to know now if these symmetry are pure gauge or not, are proper, improper, that's the language Daniel was using yesterday, we will have to consider the charge. And so when you have a symmetry, you can associate the generator of that symmetry, so this charge. And because we are considering gauge symmetry and not global symmetry, your charge won't be a volume charge, but will be a surface charge. And you have that if Q equals 0, the symmetry will be pure gauge or proper. It means that when you act with that generator on a state, it won't change the state. While if you, if it's a physical large improper, that will change the state, and that is encoded by the fact that the charge will be different of 0. How compute the charge? So here I use the covariant phase space formalism, and we have seen a glimpse of it yesterday, but let me just sketch it very briefly. So when you have an action S, that is a bulk action, you can be generalizing when there is boundary term, but okay. You take the variation and you have the symplectic potential here. And the symplectic potential, so you have the part of the equation of motion and all the rest of the integration by part that you will do, that will give you the symplectic potential. And from that, you can compute the symplectic current, that it's the, that you act with a delta on your theta and you anti-symmetrize. So this delta is acting on the field space. And so you, yeah. And you take the charge will be given, the variation of the charge, actually, that's what you will get from this K that satisfy this relation here. You have a whole procedure to compute the charges, and precise expression are in the literature. And the problem is like the charge diverge for Bondi gauge. So what do we do? As it was already shown yesterday, we will play with a normalization procedure, and we will play by ambiguities that you have by defining certain quantity. So first of all, your action here can, if you want to have the same equation of motion, you can always shift, you can always add boundary term. They won't modify the bulk equation of motion. So that's the A ambiguity here. But also defining this, this A ambiguity, as you see, because at the end of the day, you take this anti-symmetric variation of deltas, this ambiguity won't have any impact on the charge, just on the action. And the one who might have an impact, who might have an impact over the charge is this D of Y, because indeed, if you add D of Y, a corner ambiguity here, that won't change the bulk action, but still it can stay there until you get the charge. So that will be the program. And first, I will talk about the renormalization of the action before talking about the renormalization of the sympathetic potential and infinite the sympathetic charge. And why we want a renormalized action is because you have the result that a non-shell action, you can see it as you wanted to give the free energy of your system, the thermodynamical Gibbs energy of your system when you evaluate it for a solution. And so in that case, you want that free energy to be finite. So you would like to have a finite action. That's one of the motivation to have a finite action. And here what I will mean by well-defined variational principle or normalized action is that I want my action to be finite on shell, so that I was telling you about the Gibbs free energy, for example. So you want that when you take the limit R to infinity, so when you go to the boundary, you want your action to be finite. Also, you would like to take the flat limit, so it means that you want that your action being finite also in L being the ADS radius. And also, you would like that delta S equals 0 for Dirichlet boundary condition when the boundary metric is fixed. So I mean, when you fix your structure at the boundary, you don't want any flux passing through. And yeah, that's what we will require. So here is the answer. That's the renormalized action. So what do we get? We have this term here. That it's the Gibbons-Hawking-York term. And that will guarantee that for the Dirichlet boundary condition, your action here, delta S equals 0. After you add this counter term, that will kill the R squared divergences. This one will kill the R divergences, and this one will kill the L divergences. So what are those terms? This one is very similar to the one you find in Pfefferman-Graham renormalization, the holographic renormalization by Skanderis and collaborators. And here, this V, you see that is appearing here. This R here is the Ricci scalar associated to induced metric, gamma. But here, this V, it's a vector that is this one, and it's the normalized vector that will become degenerate when you take the flat limit. So you know that IDS, the boundary of ADS is time-like, so the induced metric is non-degenerate. While in the case of null boundaries, the metric is degenerate, and the V vector is the vector will become degenerate once you take the flat limit. So that's the interpretation of this V vector. And yeah, we have a covariant expression of the renormalization of the action. So now we can go to the sympathetic potential. And so now you have to add this term that we add to the action, and you do the full procedure, so you can take off their sympathetic form. And here, the term you need to kill the Y term that I was telling you about, you need to choose it in such a way where now this V bar and gamma bar are the unphysical quantities. So it's the when you multiply the quantity by R or divided by R to get this unphysical quantity in the language of Ashtekar and so on. And what you get at the end of the day, I give it to you explicitly to convince you that my procedure worked. And you get this sympathetic potential, which is finite, as you can see, and in R and in L as well. So very good. We can now compute the renormalized charges. So we compute the charges, and that is the result. So what do we have is that you see that Y and F appear in the charge, but not omega. It means that in the Bondi gauge, the F and Y are large gauge symmetry, so are improper gauge symmetry, while this wild transformation is trivial. So it's different of what happened in the Feynman-Graham expansion, as we have seen yesterday, that in odd dimension, you have a charge associated to that omega, but while here the charge is always 0. So you might wonder about the integrability, and why? Because you have this result that if you manage to integrate over the field space, so you integrate this delta, so it means that you have to specify the field dependence of your Y and F. And if you manage to integrate over the field space, it means that you have an Hamiltonian that is associated to the flow generated by your symmetry Xi. And it has been shown, like in Barnish-Roussard and so on, we have been discussed yesterday about that as well, that non-integrability is related to the presence of a flux through the boundary. But here you might wonder, but what flux could it be in 3 dimensions? Because there is no there is no propagating degrees of freedom. So it looks like fake news that you will have through your boundary. And we have shown also in that case that a state-dependent redefinition of the symmetry generator will render the charge integrable. And it's not clear at all, because you have solution space depending on 5 function, and you have only 2 symmetry generator, and you want to repack all of it in terms that you can be integrable. It's a non-trivial check of our conjecture that I was presenting you before. And so the change that you have to perform is this one. So now what you take F tilde and Y tilde to be state independent. And if you do that, the charges are integrable and the expression is here. But let's first look at the algebra of this new vector. In this vector that I have defined, F tilde and Y tilde. And you have this algebra. I will discuss about the algebra actually in the next slide when I'm talking about the charge algebra. And so, yeah, you have two charges, and now we have redefined N tilde like that and M tilde like that. And if you see that if you take the boundary metric to be just the flat metric, all of that disappear, and you just have that M tilde, it's just M, and that is the charge associated to F tilde that is related to the translation along the U direction. So that's why I was telling you that is the mass, and N is the charge associated to the Y vector, which is the rotation along the phi direction. And so that's what I was telling you, that is associated to the angular momentum. So we see that at the end of the day, our space-time in Bondi gauge has 2 boundary degrees of freedom that are arbitrary function on V and phi. So the charge algebra, so that's the quantity that matters at the end of the day, because that will be the algebra under, from which the representation will, the phase space is organized with that. Okay, the representation of the charge algebra will organize your phase space, and I replug here the algebra of the vector, and you see that if you compute the bracket now, because you have integrable charges, so you can compute the bracket of the charge is the charge of the bracket of your symmetry generator and up to a central extension. And so we have a central extension in that case. And to give you a bit a flavor of that, what it is, if you impose Dirichlet boundary conditions, so you put your boundary metric to be the flat metric, and you also take that it's just a flat metric and it's still a flat metric, actually you recover the VR0 cross VR0 algebra. So the Brown-Arrow result. And if you take the flat limit, so L to 0, the flat limit is indeed well defined. And there you find the BMS, the centrally extended BMS algebra with the right central extension. So that's a very nice result. And let me conclude, and I think I'm on time. So what we have done, we have renormalized the divergent quantity in Bondi gauge for arbitrary boundary condition, except conformal compactification. We also render the charge integrable by a field dependence redefinition of the symmetry parameter, and I took the flat limit. On the paper that will go out very soon, you will also have the two-dimensional case that will be treated in the paper. But by lack of time, I think it's better that I stick only to one cases. And so I want just to finish my talk, discuss a bit about further direction and question that I have. So in the boundary degrees of freedom program that I was telling you about, I was telling you that in D dimension, we expect the maximal number is 3, is D. So in 3 dimension, it will be 3. So where is this third boundary degrees of freedom? And it means that Bondi gauge is too restrictive. The fact that you choose that gauge, you lose some information somehow. And what gauge could we use maybe to see this third boundary degrees of freedom? And one candidate can be this derivative expansion gauge. So that's one direction I would like to explore. Another, straightforward question will be, what is the generalization to higher dimension, and in particular to 4D? There have been results already in 4 dimension about renormalization and so on and so forth, but not in the full relaxing completely the boundary metric. So that will be interesting to see how our result can be uplifted to 4 dimension. The general question that has been already discussed yesterday in the discussion, it's the implication for holography. What does it mean to have this, the boundary metric that is not fixed? How you can, how holography can accommodate for this fluctuating boundary condition. And also, I think a very important line of research, it's also what is the relation about the proposal I was telling you, this boundary degrees of freedom program that I present with the corner algebra discussion that Mark Geller was presenting in his talk. And also, like, it has been shown recently in the literature, yes, that you have other charge in gravitational system. I'm thinking about this magnetic charge or dual charge for gravity that Oliveri, Speciale, Kodas, Carbotter, and Perry has been pushing forward. And it will be interesting to see how all of them can interplay and what is the relation among all of them. And also you have also the relation with the first order formalism, where the charges have been computed by Daniel and Max that Daniel has talked yesterday. So I think it will be very nice to understand how all these different charges can fit in one picture. And Mark Geller was proposing this avenue about corner algebra, and it would be interesting to see how everything takes place in this big picture. So thank you, and take care for this pandemic time.
Thank you. Thank you for the talk. So we have a couple of minutes for questions, but we already use somehow the time, but I've been flexible already with Andrea, so let's be flexible. So I have actually a question to start. So if you can go back 2 slides to the charges.
Yes, let me try. Yes.
Actually 1 slide back as well. So, okay. So these charges I'll show you the next slide. But the charges, shouldn't they be exactly given by the integrated charge Q here? If you rewrite this N tilde and M tilde in terms of the stress energy tensor, the holographic stress energy tensor of Efferman-Graham coordinates, I would expect it would be just T mu nu times Xi, which is where Xi is the diffeomorphism that you are looking at in the boundary. So because that works, that's how it works in 4 dimensions.
We have checked, and actually, if I remember correctly, the relation with performance gram, we have this. You have an extra term that depends only on the boundary metric. So we have compute TAB. I mean, the thing we expect in performance gram in terms of Bondi quantity, and we had a term extra that were depending only on the boundary metric, and I think it's if I remember correctly, it's a total derivative with respect to phi, but I was not sure that you will cancel out at the end of the day. So I mean, I can check precisely the expression and come back to you. And yeah, and come back to you with the precise answer to your question.
Okay, we have a question for Marius.
Yes, actually, it's on the same slide. The same slide that you have now that you're projecting. Just the quantities f tilde and y tilde, this redefinition that you need to perform is actually the one that arises naturally when you deal with you know, these fluid boundary fluid dynamics. This is exactly, or almost exactly, the expressions that appear in our paper with Romain, actually. At the same footing as the expressions that appear a little bit later when you write n tilde as a function of n.
It's, yeah, indeed, Marius, you're right. There is like a strong relation. And I mean, if I might add also to support your point, in the V vector that I was presenting you in the renormalization procedure, it's actually the velocity of the fluid that you will have.
Indeed.
So it's very close. And that's why my natural question will be to look at what's happening in the derivative expansion to compute the charge and the renormalization of the charge, etc. Yeah, he's screaming for that, actually. I agree with you.
True.
Yeah, so there is another question from Mark.
Hi, Céline. Thanks for the really nice talk. If you can you please maybe go one slide forward? I think.
Yeah.
It's yes. So here at the end of the calculation, you took a beta and phi equals 0, and you also, and that's this is what gave you the Virasoro or the BMS algebras. So do you expect that in the general case you will get as your charge algebra the current algebra of the isometric group, like Daniel was mentioning, since this is what you get with the most general ADS or flat space boundary conditions?
Here, the fact that you don't have a charge associated to omega, I have less freedom to okay, if you take the most general case when you have 3 charges, we have shown that you can indeed make a change of slicing in the phase space and you reach this current algebra plus a diff S1. But here, the fact that I don't have this omega, I'm not sure I will be able to reach. I have only 2 generators, so I'm not sure how much what I can get. So the question is, I'm not sure. But yeah, it's worth digging what kind of other, yeah, okay. What I want to say is that the choice of my parameter is not unique. You can find different integrable slicings for your charge, integrable basis for your charge. And I'm not sure we can get this one in the Bondi gauge. Maybe you have to go to another gauge like derivative expansion when you will have more freedom to get the charge, the algebra you're mentioning. So I'm not sure.
Okay, thanks.
Okay, I don't think there are other questions. So let's thank Céline.
Thank you.
And let's break for 10 minutes. So we resume at 11:20. So see you soon.